My name is Ron Lang. I'm a staff reservoir engineer with Knowledge Reservoir in Houston, Texas. I was assigned the task of creating a reservoir simulation model for the Rob C. gas sand. Working with me was Ken McMillan. He's a contract geologist for Knowledge Reservoir. Ken created a Petrel static model, which was the basis for the reservoir dynamic model. Ken and I were provided data from the other team members from which we created our models, and going forward with a simulation model, Brandon Mathern and I worked independently in that Brandon used the classical reservoir engineering methods to calculate volumetrics and recoveries, and I in turn used the Eclipse simulation model to arrive at volumetrics and recoveries. To get started with my presentation, I'm going to refer you to the technical brochure and the section that's titled Knowledge Reservoir Rob C. Simulation. In this section, I'll provide you a general overview of the modeling work, but for detailed analysis, I'll refer you to Knowledge Reservoir's technical report. The first page we'll look at after the section title page is the Rob C. Study Objectives and Modeling Workflow. On this page, you'll find 5 steps that were taken to construct the models: data input, static model, dynamic model, and production forecast. For data input, the data were obtained from maps, well locations and trajectories, log analysis, core data, production and pressure history, and well completions. The static model comprises the structural model, the zone model, the facies model, the rock properties, and the export files to Eclipse. After receiving a static model from Ken McMillan, I was ready to proceed with the dynamic model. For the dynamic model, I provided the PVT tables, capillary pressure table, relative permeability table. Then I initialized for the original gas in place, and then proceeded to history match production and pressure by well. After history matching, I was ready to proceed with the production forecast, which included 1 producing well and 3 drilling locations. The first image I would like to show you is the one titled Structure Model, based on 3D seismic interpretation and matched to well tops. This image comes from the Petrel model, and it gives you a general feel of the contours, well locations, and the gas-water contact. The next image I want to show you is the key input for reservoir characterization. It represents the deposition facies, rock properties, and reservoir subzones. This facies profile comes from the A-stop number 2 well, and it divides the facies into 4 groups: clean sand, shaly sand, shale, and cemented sand. I want to draw your attention to 2 shale intervals that are relevant to the upper A zone, from which the production and upside are located. The first interval is a thin shale located at about 5545 TVD. What's important about this interval is that this shale is discontinuous in the reservoir, so it doesn't have a significant impact on the production or the upside well locations. The second shale interval is much thicker and is located at the base of the upper A. Now this interval is continuous throughout the reservoir, and it provides a good separation between the upper A and the lower A. This shale separation also plays an important role in the drive mechanism of the upper A, which is predominantly a depletion drive mechanism. At the time of the study, the cumulative field water was about 16 barrels per million. And what you're going to see in the detailed reservoir simulation report of Knowledge Reservoir is that you'll see a water encroachment that is predominantly edge water rather than bottom water. The edge water encroachment was complicated by the lateral and vertical heterogeneity in the reservoir. This is one reason why it was difficult to history match the water in Eclipse. Various problematic well histories also added to the difficulty of history matching the water. The next image is the stratigraphic cross-sections southwest to northeast. This represents the facies profile of several wells, and it gives you a little bit better indication of the heterogeneity in the reservoir. The next image is the sidewall core data used for relating log porosity to reservoir permeability. The plot of sidewall core porosity versus permeability was used to develop the algorithm to populate the Petrel model with a distribution of permeability. The next image is the export grid and properties from Petrel for input to reservoir simulation. It shows several properties that were exported to Eclipse, and it also gives another indication of the heterogeneity of the reservoir. The next image is a page titled Reservoir Simulation, where we will now focus on the dynamic model. This page reflects the rock and fluid properties in Eclipse. First, we have the reservoir properties, which were exported from Petrel. They are net to gross, porosity, and permeability. Next, we have the PVT fluid, which was based on lab analysis of the number 2 well. It includes gas, water, and fluid densities. Then we have the relative permeability, which comprises the capillary pressure curves based on lab data available in 4 samples, and relative permeability curves based on analogs. The first image regarding the dynamic model is the Eclipse initialized volumes. This image represents the gas distribution in the model. The initialized model reflects an original gas in place of 199 BCF of gas. It's based on a gas-water contact of 5,607 feet with initial water saturation of 24.3% and initial gas formation volume factor of 1.096 reservoir barrels per MTF. The next image is titled Relative Permeability and Capillary Pressure. This page contains 2 images. The one on the left is water-gas relative permeability, and the one on the right is capillary pressure. Special core analysis data were not available for the water-gas relative permeability. The curves are based on capillary pressure data and reasonable assumptions for a gas-water system. Please refer to Knowledge Reservoir's technical report for a discussion of the endpoints. The capillary pressure curve is a plot of height above free water versus water saturation. The initial water saturation of 24.3% is based on the saturation at the top of the zone, which is 139 feet above the free water level. The water saturations on the curve between the top of the zone and the free water level were used to describe the transition zone in Eclipse. The next image represents production and pressure history match. The plot reflects gas production rate and bottom hole pressure, both measured and calculated in Eclipse. The objective in simulation history matching is to first match the gas production rate and then use that as a driver for Eclipse to calculate the bottom hole pressures. The measured bottom hole pressures are represented by the markers on the plot. The Eclipse calculated bottom hole pressures are represented by the solid blue line. As you can see from the historical bottom hole pressure, the reservoir has been in communication during its development history. The Eclipse calculated bottom hole pressures are reasonably similar to the measured bottom hole pressures, and the current calculated bottom hole pressure is approximately 1,500 pounds per square inch, and this is similar to the bottom hole pressure measured in the A7 Sidetrack 2 well. The 1,500 pounds of calculated and measured bottom hole pressure suggests that there are remaining reserves to be recovered. The next image is the proposed new Rob C wells, the horizontal wells targeting the upper zone. You'll see a top view and 3 profile views of 3 proposed lateral wells. Ken McMillan proposed to place these horizontal laterals at the top of the structure and on strike. He also placed these laterals above the discontinuous shale interval that I spoke about earlier. The reason for placing these laterals above the discontinuous shale is to try to stay away from the water as much as possible. The next 2 images represent the simulated field recoveries to August 31, 2025 for the Rob C reservoir. They include the P90, P50, and P10 cases. The first image represents the minimum case forecast, which is the P90 case. You will see 2 tables and 2 plots. The 2 plots reflect the gas rate, gas cum, and reservoir pressure. The first table represents the field volumes and recoveries. They are the gas in place, condensate in place, the cumulative production and remaining recoveries as of February 28, 2011, the ultimate recoveries, and the gas recovery efficiencies as a percent of gas in place. The second table reflects the remaining recoveries by well as of February 28, 2011. The P90 case is based on 2 criteria. First, the maximum capacity rate is limited to 10 million cubic feet per day per well. Secondly, the recoveries are estimated against 550 psia minimum flowing bottom hole pressure and 50 psia minimum separator pressure, and the P90 case assumes no damage to the laterals. The second image reflects the simulated field recoveries for the P10 upside case and the P50 most likely case. The criteria for the P10 upside case are the maximum capacity rate of 10 million cubic feet per day per well and recoveries estimated against 50 psi minimum separator pressure, assuming no damage to the lateral and no minimum flowing bottom hole pressure. The criteria for the P50 most likely case are the maximum capacity rate of 10 million cubic feet per day per well and recoveries estimated against 85 psia minimum separator pressure with no minimum flowing bottom hole pressure. For the P50 case, we are assuming lateral damage, that is, only 50% of the lateral contributing to flow with a skin of 10. I would like to reiterate what I stated in my introduction, and that is Brandon Mathern and I worked independently. While doing so, we both arrived at similar volumetrics. Thank you for listening to my presentation.